We will start now. And the goal for today discussion is to talk about function approximation. So function approximation is basically, you can call it a theoretical machine learning. People study function approximation in the machine learning community. And I know many of you are aware of transformers and neural networks and so on. So what I'm going to tell you is how can we apply some of those tools and techniques that people have developed in the machine learning community over the past 50 or 60 years? How can we apply that theory to the dynamic programming setting that we are currently interested in? So remember that originally the problem statement that we started with is I have xt plus 1 is a function of xt ut. T goes from 0 to capital T. I have a performance index ju, which is ct plus 1 xt plus 1 plus summation t goes from 0 to t ct xt ut. You can write it j as a function of u or j as a function of pi. So let me write it j as a function of pi. But it doesn't matter how you want to write it. It really depends on whether you're looking for an open loop action, set of actions, or you want a closed loop policy. And so far, what we have discussed is if you want to solve this problem using dynamic programming, you have to do the following. You have to define Vt plus 1 equals to Ct plus 1. So the terminal value function is the same as the terminal cost function. And then Vt of xt is argmin. No, Vt is, I also have a constraint gt of xt ut less than equal to 0. So this is the constraint that my action always has to satisfy at every state xt. This is the only set of actions that I can pick, and this has to be satisfied for all t in 0 to capital T. And the constraint dynamic programming algorithm was as follows. Let me just write it here. I know it will be a bit tight, but let's do it. Vt plus 1 of xt plus 1 is the same as ct plus 1 xt plus 1, and Vt of xt is minimum over ut of ct xt ut plus Vt plus 1 composition ft of xt ut such that gt xt ut is less than equal to 0. And this ut is in Rm. So xt is in Rn. Ut is in Rm. And then I want to compute pi t star of xt. This is the argmin of the same thing. Okay, so this is what we have studied so far. Yes.
When I was doing the problem 201, I was thinking whether we can get rid of the terminal cost. Instead, we just constrain the state action of the terminal using constraints.
So in the MPC setting, we had the constraint of the terminal terminal state, and then what we did was we added a terminal cost function. That was the soft constrained MPC. Right? So your question is, can we replace the terminal cost with a constraint?
Yes.
Not quite, because terminal cost is completely different from constraints.
Oh.
So gt of xt ut is completely different from ct plus 1. right? So generally speaking, you cannot really replace cost with constraint. Well, okay. You could always construct a situation where you can replace it, but in general, cost is cost, constraint is constraint. And constraint comes from the physics of the system, biology of the system. So, my body is not that I can lift this table up and move it somewhere else. That's the constraint I have. So my actions are constrained by my current uh, body, like whatever the state of my body is, right? So that's the constraint. The cost is, I don't know how much I'll charge for moving it from here to there, right? So the cost and constraints are completely different quantities.
So constraints are more like a general property of a system.
Yeah, it has to come from physics, chemistry, biology, economics, whatever, something like that. So I have a budget constraint. My battery pack has constraints on how much current I can put in there, and so on and so forth. So that's the constraint. The cost is typically energy, how much energy I'm going to consume, how much money is it going to cost. So, yeah, so the two are completely separate quantities. And you can sort of imagine that somehow you add the Lagrange multipliers multiplied by this constraint and you can add it to the cost function and all that stuff, but then you need to know what the Lagrange multiplier looks like. And generally speaking, you don't know what the Lagrange multipliers are going to look like. But in some sense, Lagrange multipliers is the connection between the cost and the constraint. And yeah, so not sure how you want to think about it, but that's how I think about it. Okay.
Thank you.
Any other question on this? Okay. So what have we discussed so far? We said that if T is extremely large, then I have to cut down this T. And the way we did that was using MPC and rollout algorithm. Those were the two algorithms we talked about. And within MPC, there is soft constraint MCP and there is MPC, and then there is a hard constraint MPC, which we talked about. The second problem was if my state space is very large, so this N is extremely large, then solving this problem, applying this dynamic programming becomes extremely complicated because with high dimensional xt, the curse of dimensionality kicks in. What that means is now you have to discretize xt over a much larger space. So the number of discrete points is going to be extremely high. So it's going to be very costly to solve this dynamic programming problem. And so what we did was we studied differential dynamic programming, we studied LQR, and we studied singularly perturbed optimization for singularly perturbed system. And that allows you to somehow reduce the complexity of the dynamic programming equation, wherein instead of solving a dp over a very high dimensional problem, you are now solving dp that is much simpler in nature. So you were either doing cost approximation or you were doing model approximation in that particular setting. The third topic that I'm going to touch upon today is the approximation of the value function or policy. And the philosophy, so I'll just first talk about the philosophy of this. So at every point of time, if I want to compute this Vt, I need to be able to store Vt plus 1 in the computer. Okay? Because I'm doing all of this computation on a computer, right? I'm not doing it in my head. So I need to be able to store this Vt. So what is the typical way by which you want to store a function in a computer? So if I were to tell you, I have a function summation of ai sine omega it, I goes from 1 to n. This is a function of, well, I'm using f. Okay, I'm going to use g. No, g is also used. h is not used right now. Yeah, okay, h is not used. So this is my function. I want to store this function on a computer. How would you store it? If this is the function, how do you want to store it in your computer? Yeah.
Compute the values and store a table.
Okay, wonderful. So So idea number 1, compute the value at what t. So this is h is a function from r to r. So what t do you want me to pick? Suppose we have unlimited computational power. So computation is not our limit today, right now, for idea number 1. So what would you want to do?
I'll just sample at a constant
Interval?
Yeah.
Can you tell me what is the constant interval you are going to pick? So you will pick a set T, which is a subset of R. Let's say T is going to look like T1, T2. Will it be an infinite sequence or a finite sequence?
It should be finite because this should be
But this is from R to R, right? So you will approximate the entire real line by just some finite number of time steps. Would it be fair to say that you want to do it from minus 1000 minus 999.9 and so on until you reach 1000? Will that be okay?
If it's periodic, we can just
Yeah, I think this idea is good. Let me go with this idea. So you are going to sample the T from this particular, like this is the way you have sampled it. And now you are going to store in a data structure, let's say the data, or maybe in an array. You will create an array of array. So this is minus 1000, f of minus 1000, then minus 999.9. Oh, not f, h. Sorry. H of minus 999.9 and so on and so forth, right? So you will have an extremely large array of array and you will be able to store this function in your computer, right? Now, remember this Vt plus 1 is being evaluated at some Ft of xtut, right? So I've stored this Vt plus 1 in this particular fashion, but in this Ft of xtut turns out to be 999.95. So I've not stored it in my computer. So what do you do?
approximate to the nearest value.
Approximate to the nearest value. So how will you approximate to the nearest value? It is 999.95. So will it be minus 1000 or minus 999.9? You can take the average. So you will do the linear interpolation between these two values and then you can pick the whatever the interpolated value is, right? Okay, so that's one idea. That's one idea, which is to sample the points. So initially I started with an infinite set. By some stroke of imagination, I converted it into a finite set. I evaluated this function at each of those finite number of points. Now, if I have to evaluate the function at some intermediate point, I can do linear interpolation, I can do quadratic interpolation, I can do whatever the heck I want to do, and I can interpolate the heck out of this function. But the problem is I can only interpolate between minus 1000 to 1000. If this one turns out to be 1001, then what do we do?
Is it possible to just to solve this equation with only one value, like the exact value that we need, instead of just solving for everything?
What do you mean by solving? I'm just storing the function right now. So I just want to store the function and I want to be able to query the function. So that's the two problems that I'm dealing with. I want to store this function on a computer, and then if I have to evaluate it at a specific t, then I should be able to evaluate the function at that specific t. And hopefully, in that process, we shouldn't be introducing too much error. But that error part I'm going to talk about later. So right now, just free up your mind of all the garbage that you're thinking about and just focus on this problem, which is how do I store this function and how do I query this function? That's it. Those are the two topics that we are going to think about today. Okay, so one idea is linear interpolation. Now my problem is I'm at 1001. I need to query. What should you do?
Maybe we can plot the whole values and see the path and make a guess.
Okay, so you will do the linear interpolation from 999.9 to 1000 and then you will extrapolate it to 1001?
No, maybe
No.
the whole function from minus 1000 to 1000, we can see the whole values of.
You have to be a bit more mathematical. So computer doesn't understand seeing. The computer understands linear interpolation. That's what I can implement on MATLAB. That's what I can implement on Python. So tell me a Python library that I can use to evaluate it at 1001, or MATLAB library or whatever, something. Yeah.
I think we can also do a Fourier transform to the.
Let's get to it in idea number 2. Okay, so don't go ahead. I'm still sitting at this particular problem. I've stored this in my computer. You told me to store it in my computer like this. I've done this. I've written the code. Now don't change the idea, because I have to go back and change my entire code. Okay, so I have to evaluate it at 1001, and computer cannot see, so I cannot apply your idea. What can computer do, and how do I evaluate it at 1001? It's a real problem, by the way. But so I want you to think about it, and even if it's a bad idea, just come up with the idea. So one idea that I proposed was, I look at this point, and then I do an extrapolation. So I don't do interpolation, I do extrapolation. So this one to this one, it changed by, let's say, 0.5. I'm going to multiply it by 1, right? That's the derivative. I'm going to multiply the derivative by, not 1, it's by 10. I'm going to multiply the difference by 10, and I'm going to add it to h minus 1000, and that's going to give me the function value at 1001. What about 1 million? I have evaluated it until 1000. I now need to evaluate it at 1 million. Because my original function is from R, so I can pick any number, any real number. So I'm picking 1 million. How do I evaluate it at 1 million? I can maybe use the same idea that I've started here. Now you see, this one is always bounded between, I don't know, summation of AI to minus summation of AI. But now I'm doing this linear interpolation, and I'm probably getting a very large value. And so therefore, I'm introducing a lot of error. So as I move away from this set, I'm introducing a lot of error in the function evaluation. So storage is easy. Evaluation becomes error prone. So maybe this idea is not good. Okay. Idea number 2. So this is how I'm storing it. And the query is linear interpolation. So not a good idea. What is idea number 2? Yeah.
If you're on MATLAB, you could use a symbolic toolbox and define the actual function, and then we could call the function and query any value of t to get the value.
Okay. So how will you store it?
In MATLAB, you're able to define variables symbolically.
Of course, yeah. So that you can do in Python as well. You can do it in C++ as well. Not symbolic, but you can define a function. So what would you do? How would you store this function? Right now, you know this function. This is what the function looks like. How would you store it? You know, it's not like we don't store these things. We store music, we store videos, we store my lectures, right? On computer, they are all signals of this type, right? And we are able to store it. How are we able to store it? Yeah.
I still think Fourier transform.
Yeah, perfect. So now is the idea number 2 is Fourier transform. So how will you store it?
It's basically just wind a very long sequence back, and it'll have like peaks. And
Tell me, today for this particular class, I am a computer. I can only understand computer stuff. So tell me how you want to store it.
Store the parameters of.
I don't understand parameters. Tell me how can I store that particular function? I'm a computer. I can understand arrays, and I can put real numbers or float 64 or double 128 in that array. So how would you store it?
Store the frequency and also the
A1 omega 1, A2 omega 2, a n omega n, right? So I've stored this, and how do I query it? So I can write h at the rate t summation of ai sine omega I t, I equals 1 to n, right? So I can write something like that in MATLAB, and you can write something similar in Python. So you can use this array in defining this particular function. Now this function has zero error from minus infinity all the way to plus infinity. No error whatsoever if I were to use this way of storing the function. Okay, so idea number 2 is great because we are able to store it exactly. And the reason why we were able to store this exactly was because I know exactly what the function is. Now I have a signal. I don't know what the AIs and omega i's look like, just like I'm speaking, and this is emitting an audio signal, and the camera is kind of recording all that audio signal. Then what do you do? So now all you see is amplitude of the audio, right? Sorry?
ATFT.
Yeah, so you do the Fourier transform. So idea number 3, if ht is not known, but ht is observed. So I can, at every point of time, I observe what the amplitude of ht is, then I do FFT and store the coefficients. Much like this particular thing. Okay, so that's idea number 3. So if I don't know the function, but I can observe the function, I can observe the amplitude of the audio signal, I can do a fast Fourier transform on the computer. So now Python has packages for it, MATLAB has packages for it. So I can do the fast Fourier transform. And then at some point of time, beyond a certain omega, I'm just going to truncate the Fourier transform. I'm not going to do the Fourier transform for all the values of omega. So for certain omegas, which in the case of humans, we can hear from 20 hertz to 20,000 hertz. So that's the omega I'll store. Above 20,000 hertz, I'm going to delete it, erase it from the memory. Below 20 hertz, I'm going to erase it from the memory. I don't care about it. So between those two omegas, I'll keep the Fourier transform, store the coefficients pretty much like this, and then I can create that signal. However, the new signal that I can create is going to be an approximation of the old signal, right? And that's called compression, right? All of us have heard about compression. So how do we compress? Well, we remove certain high frequency signals and low frequency signals that are not important and keep the frequencies that are important for our specific application. And that's what JPEG compression is and many other compression stuff that I don't know, any of you have taken a course in compression? I'm sure you have taken, many of you might have taken signals and systems, right? So you have studied some part of it, but compression is probably some graduate class where you study some of these things. Anyways, so that's the idea. So you're not storing the function exactly, but you're storing the approximate function. And storing is not the only problem. The problem is also of query, and we should be able to query it. And so given the value, I should be able to come up with how to store the function so that the query is also very simple and straightforward. It's fast, right? So query of this particular thing is also fast. Okay. Now let's go back to this particular example. So I have a function, value function, and at every point of time, I have to store the value function and I have to store the policy. I have to store the policy because I need to execute the policy. And I'm flying the flight. I have stored the stored the policy of how I'm going to pilot this particular flight in my computer. So at 500 miles per hour, I'm going to do this. At 600 miles per hour, I'm going to do this. If I have to figure out what I have to do at 550 miles per hour, I'll probably do some sort of interpolation and figure out what I need to do at that particular point of the state space. The value function is needed to be stored because value function is needed to compute pi t minus 1. So this is needed to compute pi t minus 1. So I need to store it so that I can add it to the cost function at t minus 1 and do the minimization. Minimization requires me to compute the gradient of this value function. So hopefully during the query phase, not only should I be able to evaluate the function, but I should also be able to evaluate the derivative of the function, because that's what is needed for solving this optimization problem. Okay. So important thing is I need to be able to store the value function in a way that I can query it very easily and I can take the derivative very easily. I should be able to store the policy so that I can query it. Derivative is not that important. Okay, I don't need to take the derivative of policy, but for value function, I do need to take the derivative because I have to solve it using some gradient method that we have already studied in the class. Okay. So let's go back to 1960. I'm faced with this issue. I have to send this thing to moon. Somebody has given me the trajectory that I'm supposed to follow. And now I need to store this value function around the trajectory and the policy around the trajectory. What would you do in 1960? How will we store the value function and how will we store the policy? Okay, so that is studied under the umbrella of what is known as function approximation theory. This theory is, so there is no book on function approximation theory. There is book on support vector machine, there is book on neural network, there is book on regression trees and so on and so forth. But all of this in my brain, all of this is sort of connected under this broad umbrella of function approximation theory. So I have a function, I can evaluate the function at specific points. Once I evaluate the function, I need to be able to evaluate the function at specific points. I can store that particular function. I need to be able to store that function in the memory, computer's memory, and I should be able to query the function, and sometimes I also need to take the derivative, so the function should be differentiable. So in order to study function approximation, I want to talk about the following things. So I have the initial function class. I'm going to call generally people use f, but I'm already using f here, so I'm going to use h. Then there is a parameter. This is the original function class h. I'll make these things a bit more concrete in some time. Then I have a approximating class. I am going to denote it by h theta. You have the parameter set theta, which is a subset of Rd. This is capital theta, by the way, so circle with h written in it, that's capital theta. And we have parameter, so h of theta is a function h theta from Rn to Rp. I want to be able to sample. Let me get to it in a bit. Okay. So what is the function class h? So I know from my experience that this vt plus 1 is a continuous and bounded function. Pi t star is a thresholding function. So all of that is something that I've known from my experience because I've been running these optimizations for many, many years. So my vt plus 1 could be coming from a specific class. So it could be continuous and bounded function. It could be lower semi-continuous function. It could be Lifshitz continuous function, and so on and so forth. So vt plus 1 is coming from some function class, and pi t star is coming from some function class. So pi t star could be a sequence of step functions, so it could be discontinuous functions, or it could also be a continuous and bounded function, or it could also be Lifshitz continuous function, and so on and so forth. So that's my function class h. I cannot store this function in this function class h. Okay. So can you store a continuous and bounded function on a computer? And the answer is, on a realistic computer, you can't really store a continuous and bounded function. You can store the Fourier coefficients, you can store the omegas, you can store other things, but you can't store the entire function itself. So what you do is you come up with an approximating class of functions. An approximating class of functions depends on the parameters. Okay. So so this is a subset of the, let me write it as equality. I don't want to be very complicated here. So I have a function approximating class. So I have the set of all audio signals. That's this one. I'm going to use the approximating class where my Fourier, my frequencies is truncated at 20 hertz and 20,000 hertz. So I'm just storing the amplitude of signals between 20 hertz and 20,000 hertz. So that's my function approximating class. Okay, so I'm ignoring all the high frequency signals, ignoring all the low frequency signals, keeping the signals in between. That's my approximating class, which is represented by a parameter set. So this is AIs and omega i's. Okay, that's the set that this parameter set will have. So it has a dimension d. The d could be 1, the d could be 5, the d could be 100, or the d could be 1.8 trillion, right? And where is 1.8 trillion used? It's used in all the large language models. Okay, so the parameter set could be very high dimensional or it could be low dimensional. And now I have a set of functions which are represented by this parameter, and it maps Rn to Rp. Typically this Rn is going to be the state, because that's what I'm trying to, these functions are functions of. So this is typically the state. This one is typically the value function, in which case p is going to be equal to 1. And if it is policy, then p is going to be equal to m, because my action is a vector in Rn. Okay, so this p could be m or p could be 1, depending on whether you're storing a value function or you're storing a policy. Now, how do I store it in the computer? Well, actually, I don't store the function. All I store is the parameter theta, because theta could be written in the form of an array. Remember, theta is a subset of Rd. All I have to do is form an array of dimension d, and I can store the function, and then I can query the function also, and I can hopefully differentiate the function and so on. For neural network, you have tried to differentiate it in one of your assignments. Assignment 5, question number 1 was about differentiating a neural network. So if you store the parameter, remember in that particular question, the parameter was W, which was the matrix, and you can store the matrix, and then you can differentiate with respect to X or differentiate with respect to something else, and all of it was, it made sense in the context of neural network. So, okay. So the storing becomes easy and the query becomes very easy. Okay. Now the question is, how do I know? So given a function from this function class, how can I pick a function in the approximating class? So going back to our idea number 3, I was given an audio signal. Okay, so I was given the amplitude at every point of time. I need to be able to put that into the function approximating class. And what did we do in order to go from the raw audio signal to how we are storing it? We use the fast Fourier transform, FFT. So going from the original function class, I went through some training methodology to find a function in the function approximating class that best fits the function here. And then I store the corresponding parameter. So in the idea number 3, we used fast Fourier transform to do that. So now I'm going to move away from fast Fourier transform, and I'm going to talk about it more generally within this umbrella of function approximation theory. Okay. So how do I pick the function in the approximating class? Well, I sample I sample let me write it in more general form. So x1 h of x1 x2 h of x2 x not n xk h of xk. So I have this function class, and I can always query from the function class at every point. So x1, x2 is sampled according to whatever is your favorite sampling mechanism. You can use Gaussian distribution to sample it. Alternatively, you can just discretize the entire space and you can sample it. I'm going to call this the data set D. This is my data set. And then I'm going to solve this problem theta star equals argmin theta in capital theta h theta of x one over k I equals 1 to k h theta xi minus So many months ago, we talked about least square problem, how to solve least square problem. This is how the least square problems are set up. This is the origin of least square problem. So I have these data set h of x1, h of x2, h of xk. I plug it in here. I'm finding the best fit within this function approximating class h theta evaluated at xi, and I solve this minimization problem with respect to theta. You can pick different metrics here. So I'm picking L2 metric. I'm picking the usual Euclidean metric here. But you can be more fancy and you can pick P norm or whatever is your favorite metric when you're trying to do this function fitting. So this theory is pretty vast. A lot of people have picked a lot of different loss functions. I'm just going to use L2 here, but knowing well in advance that many people have studied completely different sets of loss functions for doing this function fitting. So this is known as function fitting. Okay. Is this idea clear? What are we doing? So I want to be able to store the value function. The value function comes from some function class, continuous and bounded function or Lipschitz continuous function. I have a function approximating class, which is indexed by a parameter set. I'm going to create a data set and I'm going to do the function fitting using that particular data set in order to find theta star. Once I find theta star, I'm going to store it in the memory. And at the time of query, I'll pull theta star from the memory. I'll pull the function form of h theta from the memory. And I'll plug in theta equals to theta star. Now I have the function ready. I can start querying it. Or if I have to differentiate it, I'll write another function that uses theta star to differentiate the function and compute gradient of h theta star. So all of that can be done very easily on the computer. Okay, I'm saying very easily in retrospect. So there was a time in 1960 when it was extremely difficult. Now we have PyTorch, we have pandas, we have a whole bunch of packages to solve this arg minimization problem, to solve this minimization problem, and to be able to store and query very quickly. Okay. Any questions so far before we proceed? Okay. So now my goal is to tell you what are the different types of function approximating classes that people have studied in the past. So there are, broadly speaking, three classes that you worry about. The first class is parametric versus deterministic versus randomized. Continuous versus discontinuous. Okay, so parametric function approximators are yeah, let me not get into the theory here, but the idea of parametric function approximators are that if your distribution of the data comes from some parametric class, then the function approximator would have extremely low error in order to fit that particular parametric class of data distribution. Non-parametric function approximators typically can approximate functions coming from arbitrary distribution. However, the differentiation between them is extremely thin. So I'm not going to be very pedantic about whether we are doing parametric function approximation or non-parametric function approximation, but I will give you examples of both kinds of function approximators, so that way you will know what the differences are. You could have deterministic function approximator, which means h theta is a deterministic quantity. You could have randomized function approximator, whether some parts of theta are completely random. Okay, so that's randomized function approximator. So you still find theta star, but some part of theta star is random, some part of theta star is coming from this optimization problem. Okay, so that's randomized function approximator. And then you could have continuous versus discontinuous, which means that this h theta would be a continuous function of xi, or alternatively it could be a discontinuous function of xi. So a discontinuous function of xi could be like step of xi. So it's equal to 0 if xi is negative, and it's equal to 1 if xi is positive. So wherever you have this h theta of xi, which is a discontinuous function of xi, then that's a discontinuous function approximating class. Otherwise, if this is a continuous function of xi, then it's a continuous function approximator. Okay, so I'll give you some examples of parametric function approximators, randomized function approximators, and I'll comment. I'm mostly going to comment about different types of function approximating classes that people have studied, and how does that fit within this particular framework. Okay, any questions so far? Wonderful. Let's look at the first function approximating class, which is linear. So h of theta summation of theta I pi of x, I goes from 1 to d. This is known as a feature vector, feature function, and these are the weights. So here the parameters are the weights itself. So remember when I had written ht equals to summation ai sine omega it, this is the same as saying theta I1 sine theta I2 t. Okay, so this is sine of theta I2 t is my theta phi t. So that's the feature function. This is the feature function, and this is the weight that I'm adding it up. Okay, generally speaking, in the context of audio signals and so on, sometimes you will have theta I2 t, like sometimes you will try to optimize this value omega, or alternatively you might just pick omega to be 20, 21, 22 hertz, 23 hertz, 24 hertz, and so on and so forth, and all you are doing is just figuring out what theta I should look like. So that's linear function approximating class. Linear function approximating class is extremely easy to train. Okay, solving this optimization problem is a least square problem. It's a quadratic optimization problem, and you can use conjugate direction method to solve this problem. Right? Remember we had studied conjugate direction. I hope everyone remembers. Right? So you can use conjugate direction method in order to solve this. If you have a problem of this type where feature function doesn't depend on theta, in which case this boils down to a quadratic optimization problem, and you can solve it fairly easily. The second one is neural networks. The function approximating class here is very complicated. So h theta of x is W3 sigma W2 sigma W1x. This is a 3-layer neural network, and you can add as many layers as you want, and theta here is W1, W2, W3. And sigma functions are typically ReLU, tan H, sigmoid, etc. Okay, so this sigma function is element wise. You're applying the same function at every element of this vector. So W1x is a vector, W1 is a matrix. This is a vector. You apply this function sigma at every element of that particular vector. Then you multiply, then you get a vector multiplied by another matrix. Then you apply sigma at every particular element of that vector. Then you multiply it by a matrix that gives you h theta of x. So this is a 3-layer neural networks, layer 1, layer 2, layer 3. You can have n layers neural network, in which case you will have n such matrices, and you will store them, and that's your parameter theta. I know that many of you don't know about this ReLU function and tanh and sigmoid, but you can go to Wikipedia or some other source and you will be able to figure out what are these different activation functions that people have used. There are tons of different sigmas that people have used in the neural network literature. Okay. Has anyone trained a neural network in the past? How many of you have trained neural network? Okay. Others have not trained a neural network before. Okay. So that's fine. I think this particular so you can look up different values of sigma. We are not going to be training neural networks in this class, so I don't want to go into it, but certainly there are many examples of sigma that are there in the literature as well as on Wikipedia. So you can take a look at those. The third one that I want to talk about is regression tree. And the simplest regression tree would be of this type. H theta of x is summation theta I1 indicator function of phi Ix less than equal to theta I2. I goes from 1 to D. So this is again a feature. So what is the indicator function? So indicator function of phi X less than equal to theta, it gives you 1 if phi X is less than equal to theta, and 0 if phi X is greater than theta. So it's kind of a step function. So that's the simplest regression tree, and it has, you pick a bunch of step functions and then you add them up together, and that gives you the function approximating class. Function in the function approximating class. Any questions so far? Now the question, the key question, which one is a discontinuous function approximating class? This one, right? This one is discontinuous. So by construction, this one is a discontinuous function approximating class. What about this one? Is it continuous or discontinuous? So if sigmas are continuous, it's a continuous because it's composition of continuous functions. If sigma is discontinuous, then it's a discontinuous function approximating class. Generally speaking, sigmas that people use are all continuous sigmas. So therefore, neural networks are continuous function approximating classes. In fact, if sigmas are differentiable, then this is also a differentiable function of x. What about linear function approximator? Is it continuous or discontinuous? So if each of these feature functions are continuous, then it's a continuous function approximator. If any of the features are discontinuous, then it becomes a discontinuous function approximator, right? So there is a lot of things to play around here. You can define the feature function as you like. You can have this regression tree kind of function approximating class in case, but then these feature functions have to be decided carefully. So in the older days, so if you go to 1970s and 80s, people would spend months trying to figure out what is the right phi to pick. Okay. Now, if you go to image processing community, they will learn about edge detectors, blur detectors, and this detector and that detector, right? So those were the feature functions that somebody carefully handcrafted. That okay, if this is the image, I move the image, I subtract it. If you see a big jump, then that's an edge, right? So that's how they defined the feature function in that era. The more modern era, so what is modern era? 2014, 2015 onwards. So somewhere around 2010, late 2010s, people said, I don't want to worry about all these hand constructed features, because hand constructed features means I have to spend an entire year of graduate students' time trying to figure out what's the right function, what's the right feature function for solving this particular problem is. So what did they do? They started picking deep neural networks as your universal function approximators, which means no matter what problem I have, I'm just going to slap a deep neural network and just approximate the hell out of that function. So I'm going to pick k not in thousand, but in billions. So I have a billion such values in my data set. I'm going to use a 20 layer, 30 layer, 50 layer, 100 layer, 1000 layer neural network. And I'm going to train it on this particular large data set with a deep neural network. And that led to this whole explosion of deep neural network based function approximation. Uh, there is despite having that, I think there is a reason to have regression tree also in your arsenal. Actually, I don't know why somebody would use linear in today's world, but let's assume that somebody had given you this feature function from before. You can still use linear function approximators, but I don't think it's true for modern problems that you might be solving. It's true for older problems, but not true for modern problems. So that's all I have for today. In the next class, I'm going to continue our discussion on function approximators, and we'll learn a few important theorems in this particular area. Thank you.